Now let's see how we can use this 4-bit adder circuit inside a CPU. The adder circuit can be used to provide the binary addition operation inside the CPU. The addition operation will add two binary numbers and produce its sum as the output. Inside the CPU, our adder circuit will be part of a component called the arithmetic and logic unit, or the ALU. The ALU itself has a collection of circuits. Like the adder circuit, there will be a separate circuit that can do subtraction. Another circuit will be there to do multiplication and another to do division. So likewise, ALU can have many circuits depending on the type and the number of operations that are supported by the CPU. All these circuits will receive their inputs from the two inputs of the ALU, which is labeled as input A and input B. They will also share their output with the two outputs of the ALU labeled as Z and F. Z will provide the actual output, whereas F will provide some status about the output. For example, if the addition circuit results overflow to the next stage, that overflow status will be indicated through the F output, whereas the result will be indicated through the Z output. Similarly, a comparison operation might say the two values are either equal, greater than, or less than. So that kind of status output will also be indicated through the output marked as F. Apart from the data inputs and outputs of the ALU will also need some control inputs. These control inputs will tell the ALU which circuit to activate. Therefore, they are usually called as enable inputs. For example, our ALU will have a control input called add enable. This input will tell the ALU to activate the adder circuit, which in turn will receive the inputs from input A and B of the ALU, calculate the result and send that results to the Z output. If there was any overflow to the next stage as a result of this calculation, that overflow status will be indicated through the F output. The two inputs that we are going to add using our adder circuit in the ALU in fact resides in the computer's memory, in this case number A and number B. So before we can do the addition, these two numbers has to be brought into the CPU from the system's memory. And for this purpose, the CPU will use the system bus, which connects CPU with the memory. Even though we have two input numbers, the system bus can only transport one number at a time. Therefore, we have to get these numbers one after the other. Once the first number is brought into the CPU, we have to keep it within the CPU until the second number is brought in. For this purpose, we have two memory locations connected to the inputs of the ALU within the CPU. These are typically called CPU registers. In our diagram, we have labeled them as RA and RB, referring to register A and register B respectively. Registers are special type of memory locations that can hold only a single value. They are typically used to hold a value on a temporary basis until they are processed by the appropriate part in the CPU. So these two registers will also have two control inputs, which are called enable inputs again. So here there will be an enable input for the register A and another enable input for the register B. Each of these input will tell the register that there is a value available in the system bus and to copy it into itself and make it available to the appropriate input of the ALU. Similarly, we will also need another register at the output of the ALU so that we can store the output coming from the ALU until it is sent to some other device or memory in the computer. Apart from the output, any status change that happens during the operation may also be needed to be stored in the ALU for future references. For that, we have the register RF connected to the output F of the ALU. Each of these two registers will also have a control input telling them to get the value from the ALU and store it until they are dispatched to the appropriate destination. With these basic components in place, now we can see what are the steps that we need to carry out in order to execute the addition operation in our CPU. The first thing that we need to do is to tell the memory to send the first value that we are going to add, that is number A, through the system bus. When this number is available in the system bus, we need to send the control input to the register A, asking it to capture it from the system bus and store it within itself. Next, we need to tell the memory to send the second value, that is number B. When that number arrives, we need to tell the register B by activating its control input to store the value in itself. With these two values available in the two registers, the values will be visible to the ALU input A and input B. Now we can activate the adder circuit in the ALU. For that purpose, we will activate the add enable control input. The adder circuit will then calculate the output and the result will be made available through the Z output. Similarly, if there had been an overflow, that will be made available through the F output. Then we need to send a control signal to the register RO and RF, asking it to capture these outputs from the ALU and store them within themselves until they are used in any further processing step. These steps that are carried during a particular operation of the CPU is referred to as the register transfer logic or RTL of the operation. They essentially describe the sequence of activities and how data is transferred from one place to another while being processed. Each instruction will have its own RTL logic or RTL sequence. The number of steps in the RTL sequence can differ from one instruction to another. We also see that the execution of the RTL will require a carefully timed set of control signals to be sent for different components of the CPU. These timed signals are generated by a separate component in the CPU called the control unit. The control unit works based on a special input signal called the clock signal. Clock signal is special because it's like oscillator. It changes its states from active and inactive or logic high and logic low periodically at a particular frequency. In each cycle of this control, the clock signal, the control unit will generate one control signal that is required in the RTL logic. With this concept, often we use timing diagrams to show the steps of a RTL sequence. A timing diagram shows the status of all signals and the data against the clock cycle that is operating on. For example, the addition operation that we discussed right now will require 4 clock cycles to complete. And during the clock cycle 1, the system bus will have the number 1 value and the control unit will activate the enable signals to register A or enable RA to let the register know that the value has to be copied from the system bus into itself. Next, during clock cycle 2, the number B will be available in the system bus and the control unit will activate RB enable signal to tell register B to copy the value from the system bus. The third clock cycle will see the additional add enable signal, addition enable signal of the ALU being activated, telling the ALU to do the addition operation. And finally, the fourth clock cycle will activate the enable signals of the RO register and RF register, telling them to capture the output from the ALU. So likewise, this particular operation required 4 clock pulses. So the speed at which the operation can be carried out depends on the frequency of the clock. If you have a faster clock, then operations will be carried much faster because each step will be completed much faster. If the clock is slower, then operations will take more time. So therefore, the clock frequency of a CPU is sometimes seen as the main indicator telling how fast the CPU can work. But that is only one single indicator. For example, if the CPU design is such that the RTL has many steps for each operation, even at the same clock speed, that will take more time to complete each of these operations because of the higher number of steps involved. A CPU which has few steps in the RTL logic for each instruction will run much faster even at a slower clock rate because of the few operations that need to be completed out.